Ever pondered the power of the sun and its impact on Earth's magnetic field? It's more significant than you might think, especially when it comes to solar storms. These tempests of solar energy can disrupt power grids, communication systems, and even satellites. So how do we predict these celestial squalls? Enter the KP index. The KP index is our barometer for the sun's magnetic activity. It gives us an indication of how much the sun's magnetic field is perturbing Earth's, essentially serving as an early warning system for potential solar storms. However, there's a snag. Currently, the KP index is measured using a limited network of ground observatories, primarily located in North America and Europe. It's akin to trying to forecast the weather with just a handful of scattered weather stations. This narrow view can lead to inaccurate predictions, leaving us exposed to the whims of solar activity. But what if we could get a bird's-eye view of the situation? Picture a constellation of satellites orbiting Earth in low Earth orbit, LEO. These celestial sentinels could gather geomagnetic data around the clock, offering a far more comprehensive and real-time snapshot of the sun's effect. Every satellite would serve as an additional eye in the sky, providing a global perspective. This abundance of data would enable us to craft a more precise and detailed KP index, giving us a full planetary view. This isn't a novel concept. Take the European Space Agency's SWARM mission, launched in 2013, as an example. SWARM employs 3 satellites to study Earth's magnetic field. Our proposed constellation would expand on this idea, offering a denser network of data collection points. A more accurate KP index would significantly enhance our ability to forecast solar storms. This means better protection for our critical infrastructure. Picture being able to take preventative measures to shield power grids and communication systems before a storm strikes. It's about being prepared, not just reactive. With improved forecasts, we could avert widespread blackouts, communication disruptions, and the domino effect these can have on our society. By moving from a limited ground-based system to a comprehensive satellite network, we can revolutionize our understanding of the sun's impact. This not only safeguards our technology, but also fortifies a more resilient future for humanity on Earth. The potential of a satellite-based KP index system is tantalizing. We invite you to join us in exploring this frontier and help shield our planet from the sun's fury. Thank you for joining us today. If you're keen to delve deeper, you'll find links to our research paper and additional resources in the description below. Together, we can unravel the mysteries of space weather and build a sturdier future.
Hello everyone and welcome to Capstone Project 2024. Myself Ayushman Das and my project name is SolSat, the satellite. What satellite and how it works, what it does, we will see later. I was guided by Dr. Reena Monica ma'am, Professor and Associate Dean Academics. Let's dive deep into it. Let's have a brief introduction about it. The KP, we will be focusing on KP index crucially because KP index plays a critical role in understanding how the sun's magnetic field disrupts Earth's magnetic field, potentially leading to geomagnetic storms. These storms can have significant consequences for infrastructure and communication systems. Currently, the KP index is derived from data collected by a network of observatories concentrated in North America and Europe. This project proposes a novel approach to KP index determination, a constellation of satellites in low Earth orbit. This constellation will offer several advantages. First, it will eliminate the data dependency on a limited geographical area. Second, continuous data collection from multiple satellites will provide a more real-time and accurate prediction of KP index. Finally, the broader spatial coverage of a constellation will lead to more comprehensive understanding of geomagnetic activity, enabling better preparation for solar events that could impact our planet. By providing a more robust and geographically diverse dataset, this LEO satellite constellation has the potential to significantly improve our ability to predict and mitigate the effects of a solar storm on Earth's infrastructure and communication systems. Let's go to the next slide. The problem statement. So the problem statement is really simple. The current method of determining the world KP index relies on data from limited number of ground-based observatories. There are 13 observatories spread across North America and Europe, and there's one in Australia. This leads to a potential gap in global geomagnetic activity monitoring, because when we are focusing on North America and Europe specifically, we are missing out on a lot of region. We have Asia, for example, Africa, for example. We have a lot of geographical area which we are missing out. So, this potential gaps in global geomagnetic activity monitoring is existing at this point of time. There is a need for a more accurate and real-time KP index to better prepare and mitigate the effects of solar and geomagnetic storms on Earth's infrastructure and communication systems. Exploring the feasibility and benefits of deploying a constellation of FPGA-based satellites in low Earth orbit to continuously log geomagnetic data could provide a comprehensive and all-encompassing KP index, addressing the lack of a geographical diverse dataset for a geomagnetic activity. Essentially, I mean to say that when we have a constellation in low Earth orbit revolving around Earth, uh, we have an upper hand in determining the KP index because now we have an all-round geographical coverage of the Earth. Uh, let's dive into methodology and the protocols used in this project. I have used FPGA. Now, what FPGA means is the full form stands for Field Programmable Gate Array. Why I have chosen FPGA? This is because it is reprogrammable. Okay, why do we need reprogrammable and why FPGA is used? Why I have chosen FPGA to be used in a space application? There's one problem when we are talking about satellites. Uh, and especially the satellites which are predicting KP index, they need regular updation of their softwares, and there may be some course correction, and so on and so forth. There are some use cases which needed to be reconfigured from the core, and for that reason, we have chosen FPGAs because if something bad happens or something we need to update, we can just sit in ground station and update it in the FPGA. So the project employs an FPGA for real-time tasks such as data processing and satellite control algorithms. Then only FPGA cannot measure the magnetic data, right? So we have taken magnetometer, an HMC 5883L magnetometer chip, so that this magnetometer measures Earth's magnetic field in three axes, X, Y, and Z. This data will be processed in the FPGA board and will give us the horizontal component of the Earth's magnetic field, which then will be used to predict the KP index. These are the hardware components. These two are the hardware components. The rest is basically software. Then we convert the data, the raw data, the directional data that we get from magnetometer, from the magnetic compass sensor. We convert that into the magnetic data, the horizontal component of Earth's magnetic field. From that magnetic data, we convert that into a local K index. And the last but not the least, satellite constellation. A constellation satellite in low Earth orbit is proposed for continuous geomagnetic logging and real-time KP index determination. Right now, in this project, immediately we are not covering the constellation part, just because it is ambitious and it is in future. So we will just cover to the data conversion part, and we will see how we are getting the K index, local K index from the measured information. This methodology aims to improve the accuracy and real-time capabilities of geomagnetic monitoring, which is crucial for predicting and mitigating the effects of solar storms on Earth's infrastructure. Let's have a look at the methodology diagram. Here I have an HMC 5883L sensor, and I have connected these to the Ping Z2 FPGA board. Xilinx Ping Z2 is an excellent board. The programming is done via the via the Jupyter notebook. Here, as you can see, I have connected all these pins to Raspberry Pi pins according to their register and the usage. The sensor data that this collects will be sent into the serial output, and it will be stored. From that serial output, I'll be using a conversion code, which will then help us to get the local K index. This one is a data conversion diagram. This is purely software. From the raw data, I take the data, and then I use the data to convert it into magnetic data, the horizontal component of Earth's magnetic field. Then I use a conversion table. Let's have a look at what this conversion table is. I hope I can zoom it. This conversion table is an official conversion table on the historical KP index data that is available, and this is released by Uppsala University. Uh, this is released by the Observatory of Uppsala, and I have taken this data set into this conversion table into account because Uppsala is the closest observatory that is there to India. So with this conversion table, I get the local K index. Like I use that in the conversion code, and then I get the local K index graph. This is the so when we come to results in simulation, we just need to know that we are not making a satellite here right now. We are just trying to improve the core of the satellite to get the most accurate data that is there. For now, we have connected ping Z2 board to the magnetometer and we are logging the data. This is the logging data that is available. So as you can see in X direction, there is 519, Y is 27, Z is 1. And what is the unit? It is in microtesla. The heading is 43.67, and what is this? It is in degrees. It is the inclination of Earth at that point of at the point of magnetometer. Then this is a code which converts the magnetic data. Let's suppose this is the average data, right? If you can see, this 519, 519, it's repeating. So the average data is 519, 27, and 1 with the heading of 43.67. Fine. So this is the magnetic field that we get, 519, 27, and 1 microtesla. Now I need to convert this magnetic field into the horizontal component of magnetic field. I use Pythagoras theorem to get the combined horizontal field strength, that is 519.70183, and so on microtesla. So this is the conversion code for the horizontal component of magnetic field from the HMC 5883L magnetic compass sensor. Let's move on. This is the table that I was talking about. This is the table released by Observatory of Uppsala, and as you can see, there are 3 groups. Now let me explain what these 3 groups are. So JFND means January, February, November, and December. MASO means March, April, September, and October. MJJA means May, June, July, and August. Do you see any similarity here? Yes, JFND means January, February, November, December, and all these 3 months are in winter solstice. MASO, March, April, September, and October are in equinoxes, and May, June, July, and August are in summer solstice. So we have different conversion tables for different time of the year. So if we are logging in data, magnetic data in the month of April, let's suppose, it will have a different conversion table, and like for every other month we have different conversion tables. So let's see the result. Now I used a sample magnetic data, one sample magnetic data of entire day, on different groups. Like for JFND, I use the data set that I've used for JFND is the same for MASO and MJJA. Now let's see what is happening. So as we know, KP index is it's not a very complicated index. We just have to simply see the level that the graphs are reaching. It is measured from 0 to 9. If it is above 5, then we have something to worry about. But as we can see, the sample data that we took on the month of on one given day in the month of January, February, November, or December, this is reaching just below 5. So KP index is measured in once in 3 hours. So as you can see, each graph is presenting the reading of an hour. So this is one index, this is one index, this is one index, and so on and so forth. So as you can see that it is not even exceeding 5. Let's go and see the equinoxes. Equinoxes is even better because we can see that it is even reaching below 4, and the graph you can see it is similar because we are using the same data set. Then let's see for MJJA. It is kind of similar to JFND, but still it is not going beyond 5. So but with this, we see that local K index measuring is really simple. We just need to have the data per day. Conclusion. So the proposed satellite constellation LEO will enhance our understanding of Earth's magnetic field, which we discussed obviously, and it is obvious by now, offering real-time and global data. This leap forward from ground-based observatories to a comprehensive satellite network will greatly improve predictions and preparedness for solar storms, safeguarding critical infrastructure and communication systems against geomagnetic disturbances. So this was it. For this project, we are just covering the part of collecting data and converting that into local K index. In future, we will have to make the spatial recognition system of the satellite plus the flight controls of the satellite, and with this, we will be ready to launch the satellite by end of 2026 if the rate continues. So these are all the references that I have used, all the research papers and all the journals that I've used to get the idea for this. Thank you so much for your patience, and I hope this project sees the light of the day.